Yeah. So for the propellant, we have a C star of 1650 meters per second, and the gamma function is given as 0.65. Now it is given that the equilibrium chamber pressure is 7 megapascals and linear burn rate. So we have burn, burn rate law as a p to the power n, where n is given as 0.3. So now it is asked that we have to find the equivalent length for the rocket motor. So can somebody tell what is the formula for L star? How do we calculate L star for a rocket motor? Uh, Anybody would like to answer this? Okay, so L star is given as the volume of the rocket cavity motor, the combustion chamber, divided by the throat area. So initially, the area that is there, the volume that is covered by the rocket motor is this diameter, this volume into L, and the throat area is given by pi by 4 d throat square. So if you plug these values, so pi into 0.1 square into 0.2 divided by into 0.25 into 0.25 into 0.05 square. So if you find the value for this term, so you will get as 0.8 meters, which is there in this answer. Okay, so next thing is we have to find what is the characteristics time for the rocket. So anybody know what is the formula for the characteristics time? Okay, so TCH is given as L star divided by gamma square into C star, which has a unit of meters divided by meter per second, and this is unitless, so which will give you the unit for seconds. So TCH we can calculate, since we know L star from our previous calculation, which is 0.8. Gamma is given as 0.65 and C star is also given, which is 1650. So if you plug these values, can somebody calculate and tell what is the value for TCH? Can somebody calculate this value and let me know what is the value for this? Okay, so you'll get the value as 1.148 seconds, milliseconds. Okay, so let us move to another problem where we have to find what is the non-dimensional time required to reach 90% of the equilibrium chamber pressure. So this is the problem which deals with the pressurization process. So the characteristics, the non-dimensional time, which is given as the actual time divided by TCH, is just the ratio of 1 minus P, okay, P ignition by be uh, p bar to the power minus n and minus n. So so P ignition, it is given that the initial pressure of the rocket chamber after flame spreads is 1 megapascals. So P ignition is given as the pressure at the ignition point divided by the P equilibrium. So P equilibrium is given in the problem, which is 7 megapascals. So this will be 1 divided by 7. Similarly, P bar is what we want to calculate. So what is given? Say it is given that 90% of the chamber pressure should be achieved. So this should be P by P equilibrium. So this you will get as 0.9. So if we plug the values, 1 minus 1 by 7 to the power 0.7, because n is 0.3, which is given in the problem, and this is 0.9 to the power 0.7. This is T equilibrium, the non-dimensionless time. So if you calculate this non-dimensionless time, you will get the value as 2.35. Okay, so right, so let us move to the another problem where it is asked what is the so this is the non-dimensionless time. So now what we have to do is you have to convert this non-dimensionless time in time which has the unit in seconds. So how do we do that? So we have this non-dimensionless time. We have earlier calculated what is this characteristics time. So based on that, we can calculate what is the actual time that is required for a rocket to reach 90% of its equilibrium chamber pressure. Okay, so in a earlier case, we have calculated this TCH as 1.148, and we have non-dimensionless time, which will give me the actual time. So if you plug this value as 2.35, 1.48, so this will give me a value of okay, so let us find what is the value for this part. So this, if you calculate this, you will 1.48. So you will get the value as 2.35. So we'll get the value as 2.69. 6978 milliseconds. So in last class, we as I have shown you a video where we have seen how a rocket so if I play this video again, so this is a solid rocket motor which is being tested. So as you can see, it takes in time in orders of milliseconds to reach its equilibrium pressure. So similar to this, whatever we have calculated, it shows that the time that is required for a motor to reach the equilibrium pressure, it is in the orders of some few milliseconds. Okay, so yeah, so any questions till now? Any questions on this? Okay, so let us move to the another problem then. Uh, so we have another problem for a solid rocket motor, uh, where the chamber pressure at the time of burnout it is given, which is 6 megapascals. The uh, the volume of the chamber, so the volume of the chamber is given, which is 0.8 meter cube, and the throat area is given as 0.1 meter square. The characteristic velocity is given as 1650 meters per second, and the gamma is also given as 0.67. So we have to use above data to calculate what is the time required for a pressure uh, to fall up to 10% of the pressure at the time of the burnout. So anybody knows the formula for this? So yeah, okay. So this is given as P divided by P equilibrium. This is exponent. We have some negative times, so um, gamma square, I guess it is same, right? So so this L star C star, okay, gamma square C star uh, divided by the T minus TB. Correct. I hope you remember this formula, right? Okay. So if you plug these values, uh, so it so you will get, this is 0.1, this is exponent, this is 0.65 square. L star, we don't know, but we know what is the volume at the time of the burnout, and also we know the throat area. So L star is the volume divided by the area. Volume is 0.8 divided by 0.01, which is 80 meters. So this is 80, and this is 1650 into delta t. So if you substitute this value, you will get delta t as okay, so you can find the value. So you will get the value as 264.23 milliseconds. Okay. So I hope up till this point, if you have any issues with the solid propellant rockets, please discuss, because after this we'll move on to liquid rocket engines. Any doubts on this? I hope you all can hear me, right? Am I audible? Okay, yeah. So let us move to the another problem, which is on liquid rocket engines. Uh, yeah, before that, let me describe you different type of rocket engines, liquid rocket engine cycles, which are generally used. So one is known as gas generator. So in first place, why do we need uh, s- a cycle basically? Why can't we directly inject a propellant into the chamber? So my question is, why can't we have a system like this, where we have a fuel tank, fuel, and then we have an oxidizer, and we fed it into a combustion chamber and expand through a nozzle. So can we have a system like this? Why do we need this complicated system? Um, Please, guys, I would encourage you to take part in the discussion, because so why can't we have this type of cycle in first place? Okay, so can somebody tell what is the order of pressure that we use in a combustion chamber? What is the pressure? Okay, so to answer this, we have a pressure in orders of some, say, 10 to few hundred bars. So to give you some numbers, GSLV uses so the pressure is in the orders of 60 to 70 bar. Okay, so to have a to feed the propellant, we need a pressure difference, right? So to have a flow from fuel tank to oxidizer to the combustion chamber tank, for such system we would be needing the pressures in the fuel tank or the oxidizer tank to be greater than 60 to 70, 60 bar, right? And for this much high pressure, to store the fuel at these high pressures, we will be needing a very thick walled uh, uh, thick walls, which will increase the mass of the rocket, and and eventually it will reduce the payload mass, right? So we cannot have a system which can store the fuels in just the tank at such high pressures. Next, if we but we can have such engines where we can have uh, gas that is stored, uh, such as helium, and they are then what they do is they pressurize a fuel tank or and the oxidizer tank that can eventually push the fluid fuel and the oxidizer into the combustion chamber, and they can react. So these are known as gas fed systems. Okay, so they are relatively used where the pressure combustion chamber pressure is low. So we have low chamber pressure, but for higher chamber pressure, uh, we need a pump which can uh, increase the pressure from our the fuel tank or the oxidizer tank and pump it into the combustion chamber. Okay, so to have this, we can have different types of cycles. One of them is known as gas generator cycle, the other one is stage combustion cycle, and the last one is the expander cycle. So we have another cycle such as stage tap off cycle, uh, and other variations of this, where we can w- one is known as expander cycle with bleeding, and this is without bleeding. Okay, so yeah, so we can have different variations, but for this course we'll be dealing with the basic the rocket cycles. That is, one is known as the gas generator cycle. So in a gas generator cycle we have the tanks. Consider we have a say we have kerosene and we have liquid oxygen. So kerosene is the fuel is shown by red and oxidizer is shown by blue. So what we do is we take a part of kerosene and we take a part of oxygen and burn it into a pre-burner. Okay, so this pre-burner uh, uses combustion to increase the temperature and eventually drives a turbine, and this turbine is is connected to through a shaft to both the uh, fuel pumps and the oxidizer pumps. Yeah, it did not to be connected directly. There can be a gear train which can either reduce or increase the speed of this pump. So yeah, so in this way, the uh, the uh, the pumps are driven by the turbine, and this exhaust is directly eliminated into the atmosphere. So this is a SpaceX engine. This is SpaceX Merlin engine, which uses this concept of gas generator cycle. So as you can see, this is your combustion chamber. This is your throat, and this is your nozzle. Okay, so there is this part. I hope you all guys can see this. This part uh, uh, also eliminates some of the exhaust gases, right? This is because it uses this uses this gas generator cycle, where they burn a part of the fuel and in presence of the oxygen to eliminate this exhaust gases into the atmosphere. Okay, so in stage combustion, so there is another cycle which is known as stage combustion, which uses which instead of eliminating these gases into uh, the directly into the atmosphere or the ambient, we yeah, so after the turbine we supply this thing into the combustion chamber. So let us go through the cycle again. So we have fuel tanks. This is for fuel, and this is for the oxidizer. And the so these are the pumps. Okay, so this increases so the fuel can be at say 0.4 bar, and this this increases the chamber pressure up to say 60 bar. Okay, so uh, and also we also use the regenerative cooling for this. What we do is, since the nozzle, we have to the nozzle is a part where the high combustion gases are are thus expelled out. So this is the nozzle part, and this is a rocket engine. I This is a Raptor engine, again from SpaceX. Okay, so yeah, this uses the staged combustion cycle. So as you can see in this part, probably this is the exhaust from the turbine, which goes into the combustion chamber, uh, and and is expelled out through the combustion chamber. So yeah, so what we do is, we take this fuel pump, the fuel is pressurized, and uh, it does circulates the nozzle, and after this uh, it is fed into the turbines, where the turbine again drives them, and the exhaust that is generated from the turbine is again fed to the combustion chamber. I hope this part is clear, right? So this is what a schematic of stage combustion cycle looks like. This is again for Raptor engine, and this is again from SpaceX. Okay, so uh, let us start from here. So this is the okay, Raptor engine uses methane and liquid oxygen as the fuel. Okay, so we have two inlets. One is the methane, and one is the liquid oxygen. So as you can see, the uh, tank pressure is something like 4 bar, right? And the mass flow rate is also given 149 kgs per second. And yeah, so in this the oxidizer is also given, the mass flow rate. Can you calculate what is the mixture ratio, overall mixture ratio for this engine based on these values? So you will get the value something about 3.59, right? So uh, okay, so let us see why let us also see why this mixture ratio is taken as 3.59. So probably let us look into some coding part now. I'll show you why this 3.59 is taken as a ideal mixture ratio. So mm, let me share my screen. Yeah, can you see my screen? Okay, it's getting shared now. Yeah, can you see the screen? I hope. Yeah. Okay. So let us start. So yeah. So let us. So initially, what I am doing is I am doing a calculation for the adiabatic flame temperature, and eventually, what I will do is I'll calculate the ISP, and I want to plot this value against the uh, mixture fraction. So yeah, so let us define this. So I'm assuming that so for simplicity I'm assuming that the propellant temperature is 300 and it is fed at let us make it at yeah, it is at the atmospheric pressure. uh, Now, so let me calculate okay, let us define this phi value, which is the equivalence ratio. Later we can convert this equivalence ratio into the mixture ratio. So this is, let me define another library for using array. This is import numpy, yes, import numpy, yes, np. So let us vary our equivalence ratio from say 0.5 to say 6 or 6. Let us say it is at 4, and let us, yeah, so let us vary this. So we are using methane, this is CH4, and the oxygen is used as an oxidizer. Now let us set this, mm, let us calculate the adiabatic flame temperature. And store this thing as uh, and so what so how to calculate the V equivalent? Any idea? So last time we have seen for in the beginning classes we have calculated this V equivalent, right? So for these things, what all things we need? We need CP, right? CP for the mixture, and we need T adiabatic. So yeah, so let us calculate this. This is gas dot okay, T add dot append gas dot T CP dot append gas dot CP mass, yeah. Yeah, so let us run this. We got few values, so let us decrease the increment first. Yeah, so let us calculate what is V equivalent. So V equivalent dot V equivalent is 2 cross 2 uh, gas dot CP into T adiabatic, which is gas dot T, and there is another term that is 1 minus P by P uh, P exit by P naught, right? So I'm assuming that it is it is in a vacuum condition, so P, that term is gone. So let us append this value, and let us, so yeah, so let us convert our so where is the close? Okay. So to convert mixture ratio the phi into the mixture ratio, so the mixture ratio is just the mass of the oxidizer divided by the mass of the fuel, right? I hope in the last class we have seen how to convert interchange these values. So I hope, yeah. So let me again share the screen and let show you how to calculate uh, the how to. So we have equivalence ratio, which is phi. It is the mass of the fuel divided by the mass of the oxidizer divided by mass of the fuel by the mass of the oxidizer as stoichiometric condition, right? So we have methane and we have oxygen. It reacts to give CO2 and H2O, right? So if you balance this, you will get 2 in this side. So mass of the fuel divided mass of the oxidizer is just 1 by mixture ratio. And with this is molecular weight is 16 and we have 1 mole, 2 into 32. So this is 4. Yeah, this is 2. This is 2. So this is becomes 1 by 4. So what we have to do is to get mixture ratio, we have to yeah, this is 4 divided by 5, right, for methane. So yeah, so let me stop sharing from here and I'll again, yeah. I'll share from here now. So this is the how you do a first hand calculation for this rocket engines. How do you calculate the optimum mixture ratio? So yeah, we were having this 4 divided by 5, right? 5. So now let me plot this value. So let me take some of the code from the other part. So this is yeah. So this is should be mixture ratio and this should be V equivalent. So how do you calculate this ISP? V equivalent, so ISP is just divided by 9.81, right? So this will give you the ISP. So if I plot this, okay, uh, the supported type, okay. Yeah, uh, let us plot this value itself. So yeah, from where it is plotting these. So I hope this you can see, no? Yeah, it should be mixture ratio and it should be um, V equivalent. This is V equivalent CP mass, yeah. And if we divide, let me divide it by V equivalent is just NP dot array V equivalent divided by 9.1. Okay, gas.cp mass. Okay, so we have this formula. Okay. Mm, okay. Okay. So okay. So we have this equivalent velocity. Uh, gamma r. Okay, there should be yes gamma minus one also. So with this we have gas dot uh, Cp mass divided by gas dot Cv. This is gamma minus 1, right? So one minute. So this is minus T naught. I hope I am using. I'm not using 1 minute. So this is T adiabatic. Uh, okay. This must be correct. Okay, so you can see the peak is somewhere about near 3, right? Uh, yeah. So based on this, what we do is we take a mixture ratio somewhere about 3 where we have a stable combustion. So as you can see, so whatever we have seen, either to the Raptor engine part. So maybe I'll stop sharing it again. So as you can see, it is it is near about 3, right? So okay, so I'll stop sharing from here and I'll start the mm, right. So right, so as you can see in this Raptor engine part, uh, the uh, fuel is taken as 149 kgs per second, and the logs is taken as 536. So it gives you a mixture ratio near about 3.5. So that's why this that's why we have this values. Then what we do, what happens is, this is the pump which drives the uh, which increases the pressure, and the pressure is increased up to 886 bar. Okay, so yeah, so what so this is again fed to the nozzle where it cools the nozzle. Okay, and this heated the heated methane is fed to a the the gas generator where it is mixed with small amount of oxygen, and the temperature is increased, which drives this turbine. So this is the turbine, and after that this mixture is usually uh, fuel rich. So as you can see, this is methane rich gas is fed to the combustion chamber. Okay, so again, so this is for the methane part. Similarly, we have it for liquid oxygen. Liquid oxygen comes at 4 bar, uh, and is uh, yeah. So a small amount of methane is supplied to this where the combustion take place and the temperature is increased. This is the pump and this is the turbine. So this pump is oxygen rich in condition, the combustion products. So this methane rich and oxygen rich are fed into the combustion chamber where the combustion takes place at 300 bar. Okay, so this is how a stage combustion cycle looks like, and it gives a thrust value of 2.2 mega newton, and ISP at sea level is 332 seconds. Okay, so this is another engine, that is the stage combustion cycle. uh, Next is we have a expander cycle. So um, yeah, so we have expander cycle where we have a fuel pump again, and which is just fed through the uh, combustion chamber, and it goes to the turbine. We do not mix this thing with oxygen, so all the enthalpy that is gained is through the uh, a heat exchanger that is there in the nozzle part. Okay, so 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 in the turbine we have enthalpy drop, and we decrease the we again send this thing to combustion chamber. Okay, so this is how a staged expander cycle looks like. So this is since it has low only a turbine, and does not have any more parts, so it looks relatively smaller as compared to a staged combustion cycle. Okay, so this is RL 10 engine. Okay, this is a cryogenic engine where the liquid oxygen is fed through these lines, as you can see in this. So these are the channels which are used for cooling the rocket nozzle. Okay, so yeah, so in this thing, what they used to do is they feed liquid hydrogen into this chamber. uh, yeah, so this this cools the nozzle part. Okay, so one question: why liquid oxygen is fed? Why not liquid why liquid hydrogen is fed? Why not liquid oxygen? Any idea?
because it might oxidize the metal part.
Um, yeah, that is one of the reason. Another okay, any another reason for this? Okay, so there is so can you tell what is the enthalpy? What is the CP for liquid oxygen and liquid hydrogen? So if you compare this, since on per mass basis, liquid hydrogen will be having a higher CP, which means that the temperature, the delta T for same heat transfer will be less in case of hydrogen as compared to oxygen, right? So there is less chance that a phase change will take place. Okay, it might boil. So therefore this one of the reason why this liquid hydrogen is used instead of liquid oxygen. Okay, so this is how a expander cycle looks like. Okay, so yeah, so any questions on this till now? Okay, if not, let us move to the problems on liquid rocket engine. So let us look into a problem where we have a uh, three concept. Okay, so this is the injector plate, and we have three annular injectors which surrounds this. So this is the core part, core part, and okay. So I hope, yeah. So the propellant used is liquid hydrogen and liquid oxygen. The core has stoichiometric mixture ratio. So in this part, so okay, it will look like this. This is the combustion chamber, and we have three different parts. Okay, in the injector plate, the core has a stoichiometric mixture ratio. So in this, it is given the fuel is supplied at a stoichiometric condition. The three annular zones surrounds the core have successively decreasing value of mixture ratio. So it is given as 7, 5, and 3. So that uh, the gas in the contact with the wall are fuel rich. So this is the fuel rich gases. The mixture ratio, this is a mixture ratio at the three of three at the wall provides a better provides a barrier cooling. Okay, so since it is hydrogen rich, it provides uh, a cooling to the walls. Okay, uh, now it is given that the mass flow rate uh, of propellant uh, so the mass flow rate of the propellant uh, is propellant comprising of liquid uh, hydrogen and liquid oxygen are same in four zones. Starting with the core and moving toward the outer wall, find the overall mixture ratio and specific impulse for the rocket. Okay, so it is given that the inside part is giving you a specific impulse of 450 uh, Newton second per kg. This this gives you 4540. This gives you 4500, and this part also gives you 3 Newton second per kg. Okay, so what we have to find is what is the overall mixture ratio and what is the specific impulse of the rocket. Okay, so any idea how do you proceed with this problem? Okay, so inside this also it is given as 8. Okay, so we have a stratified mixture, right? So in this it is fuel rich, and as you go in toward the center, we have a stoichiometric mixture. So how do we calculate a uh, overall mixture ratio? Okay, so let us do this thing. So the overall mixture ratio is just the mass of the oxidizer in the complete chamber divided by the mass of the hydrogen, right? Correct, no? So this is mixture ratio. So okay, so which is mass from the core stream a mass of the oxidizer from the core stream. Mass of the oxidizer, say this is, let us number this 1, 2 and 3. Okay, 1 plus mass of the oxidizer from 2, mass of the oxidizer from 3. Similarly, mass of the hydrogen from core plus mass of the hydrogen from 2 plus mass of the hydrogen from 3, mass of the hydrogen from 4, right? Okay, so yeah, so now it is given that mass of the oxidizer from the core by mass of the oxidizer from the core is given as 8. Yeah, so mass of the 1 by mass of the 2 hydrogen is given as 9, not 9, it is given as 7. Mass of the oxidizer 2 by mass of the 2 is given as 5. Mass of the oxidizer from 3, mass of the oxidizer from 3 is given as 3. So so let us calculate this. Yeah, okay, and it is also given that the so liquid oxygen and liquid hydrogen are supplied in same quantity, uh, same in each 4 zones, right? So right, so this will give you mass of the oxidizer in the core stream plus mass of the hydrogen in the core uh, core hydrogen divided by mass of the hydrogen. So this will be 9, no, with this. So if you add +1, you will get this value. So yeah, so if I assume that this quantity is mass of the propellant divided by 4, because what we are saying is in each block the mass flow rate that is going is same. Okay, so this will be mass of the propellant divided by 4. So divided by mass of the hydrogen, this is 9, right? So with this you will get mp by 36 is equal to m of s2. Similarly, with we can find what is in the core, what is getting, what oxygen we are supplying. This will be mass of the propellant divided by yeah, this will be 8 by 36. Similarly, we can calculate using this. So this is, we can add 1, this is 2 plus hydrogen, this is 6 divided by mass of the hydrogen. So this is again, this term is equal to mass of the propellant divided by 4. So hydrogen we can calculate, this is mp by 4 into 6. Mass of the 2 in the oxidizer is mp 5 mp by 24. So let me make it, this is in the second part, this is for the core. So similarly we can use this thing. So this is So this is M2 oxidizer is 8 plus M2 H2 divided by M2 H2. Okay, so this is again MP by 4 into 8 is M2 H2. Okay, 1 minute. So there's a error here. So this is 7 was there in the this is okay, this we have numbered as 1, right? This is numbered as 1. So okay, so this will be 1 and this will be 2, the next one. Okay, so this is the mass of the propellant, then mass of the oxidizer is mass of the propellant, right, into 7, right? So we have this, right? We have for the second part, and similarly we have it for the last part. M03 plus M03 S2 is 4 S2, which gives you MP by 4 into 4. This is M3 S2, and similarly if you can calculate M3O2, which is 3 by 4 into 4 divided by MP, right? This is our fourth part. So you can club all these values into this this thing, the overall mixture ratio, and you have MP as common, so that this will get cancelled off. So if you calculate this, you will get 8 by 9 plus 7 by 8 plus 5 by 6 plus 3 by 4 divided by 1 by 9 plus 1 by 8 plus 1 by 6 plus 1 by 4. Okay, so you will get 241.47, which is 5.13. Okay, so I hope this is clear, right? Any doubts on this? Okay, so next part is how to calculate the specific impulse. So the specific impulse will be just a summation of all the ISPs, right? So it should be yeah, it will be the weighted average of the all the ISPs, mass weighted average. So to calculate ISP, this will be percentage of mass that is going. Okay, this will be summation mi by m total into ISP of that stage. Okay, so yeah, so we have 0.25 mass flow rate that is going through the core stage, which has a ISP of 4500. Similarly, the first part, the first annular ring, which has no, the first annular ring is in black, which is 4540. Okay, so again 45, I guess it is 70. Okay, it is 45, it is 4540, 4540, 4300. Okay, So this is 4540 plus 0.2545 0.25 into 4530. Okay, so if you calculate this, you will get the value as 4460 Newton second per kg. Okay, I hope this is clear to all. Is it fine?
Yes, sir.
Okay, so let us move to another problem, uh, which is on gas generator cycle. So it is given that high pressure pump with liquid propellants and rocket based on gas generator cycle has a vacuum thrust of 735 kilonewton and a burn duration of 182 seconds. So we have N2O4 and UDMH as a fuel, which has a specific impulse of 2950 Newton second per kg, and a mixture ratio is given as 1.87. The pressure in the combustion chamber is 6 megapascals, and the pressure supplied to the combustion chamber is 7 megapascals. Okay, N2O4 is stored in a tank, a propellant tank, which has a pressure of 0.4 megapascal. UDMH is stored at 0.32 megapascals. The density of UDMH and N2O4 is given as 1400 and 790. So what we have to find is what is the power that is required to drive this N2O4 and UDMH pump. So I hope we have done similar problem in the past. So uh, would you like to first try this problem out? Okay, so let us try to solve this problem. Yeah, so we have a fuel tank, we have a oxidizer tank, this is UDMH, and this is N2O4. We have a pump, that is driven through a turbine. Okay, so yeah, so we have combustion chamber, and we have the thrust. Okay, so it is given that the thrust is 735 kilonewtons. It is also given the specific impulse for N2O4 and UDMH is 2950 Newton second per kg. Okay, So the propellant mass flow rate, let us now calculate what is the total mass flow rate that is coming out through the engine. This can be calculated as thrust divided by the ISP. This is 735 10 to the power 3 2950. So this will give you the value of 249.15 kgs per second, right? So can you calculate the individual mass of the fuel rate and the mass of the oxidizer? Can you calculate this? So this is the problem. This is the problem which we have. Can you calculate based on what we have right now? Okay, so why we are doing this is because we have to find the power that is required to drive this pump for fuel and the oxidizer, right? So no, the pump power is given as delta P, the work that is given as delta P into the flow rate, right? For flow rate, we should know what is the mass flow rate of the individual propellants, and we can divide it by the density. We can get what is the flow rate. And we can just multiply by the pressure difference. We can calculate what is the work done by each compressor. So okay, so to calculate this mass flow rate of the propellant that is coming out, it is just equal to mass of the fuel and the mass of the oxidizer that is going into the chamber. It is also given the mixture ratio as 1.87. So if you take out this common, this is mass flow rate of the fuel. So this is mass flow rate of the propellant is 249.15, and we have this mass flow rate of the fuel. This is 2.87. So we have this mass flow rate of the fuel as 86.81 kgs per second. Okay, so similarly we can calculate what is the mass flow rate of the oxidizer, which is just mixture ratio into mass flow rate of the fuel, right? So this is one. If you multiply this thing with 1.86.81, you will get the value as 1.62. Oh, sorry. You will get the value as 162.34 kgs per second. Okay, so with this value we can calculate what is the flow rate. So the flow rate is just the mass flow rate of the fuel divided by the density. It is 86.81. So density of fuel, which is UDMH, it is given in the problem, which is 790, and N2O4 is 1400. So this is 790. So with this we'll get the value as 0.11 meter cube per second. This is for the fuel. Similarly, we'll have for the oxidizer, this is the density of the oxidizer. This is 162 point 162.34 34. So this is 0.11. Meter cube per second. Okay, so now we can calculate with these thing, we can calculate the work that is required for the fuel, that is the pressure difference into the, so the pressure difference between the tanks is, fuel tank is, so this is the chamber pressure, and this, the UDMH is stored as 0.3 megapascals. So into 10 to the power 6 into 0.11. So with this we will get the value as 0.735 megawatt. Similarly, we have for oxidizer, that is the pressure, the difference between the tank, this is oxidizer, which is 7 minus 0.4. So the N2O4 is stored at 0.4 megapascals. So this is 0.115, and so with this we have 0.765 megawatt. Okay, so this values are huge, no? So this is almost equal to uh, just supplying energy to a small town. This is huge, huh? So so now the second part of the problem. Okay, so the next thing is, if there is a efficiency of the pump is 60% and the turbine the turbine efficiency is 80%, so we have to determine the flow rate through the turbine. Okay, the gas generated pressure and temperature can be assumed as 3.5 megapascal and 670 Kelvin. The exit pressure of the turbine can be taken as 0.18 megapascals. Given that the molecular mass of the combustion products are 20.19 and specific heat is 1.9 kilojoules per kg, and specific heat of the product is 1.26 4. So we have a turbine turbine. So we have the gases that is generated. This is gas generator. So it produces gases of 670 Kelvin. And it is asked what is the mass flow rate that is required by the turbine to drive the pump. So first of all, we have to calculate what is the work that is required by the turbine to drive the pump, and then based on this work done, we can calculate what is the mass flow rate that should be supplied through the turbine to drive the turbine. Okay, so the total power that is required by the turbine is just equal to okay, that let us see what is the work uh, which is supplied to the pumps. So which this will be equal to work for the oxidizer, work for the work of the compressor for the oxidizer, and work of the compressor for the fuel, divided by the efficiency of the pump, right? So with this you will get, this is 735 plus 0.765 into 10 to the power 6. Efficiency of the pump is given as 0.6. So this turbine is again connected to this pump side. So okay, so this is for fuel and this is for the oxidizer. Okay, so with this you will get the value as 2.5 into 10 to the power 6 watt. Okay, so the power input to the turbine will be equal to 2.5 10 to the power 6 divided by efficiency of the turbine, which is equal to, this is given as 0.8, which will be 3.125 into 10 to the power 6 watt. Okay, now let us calculate the mass flow rate that is required for this thing. So it is given that the temperature is this, yeah, and Cp we do not know for this product, but we know gamma, right? This is 1.264. I guess Cp is should be given, no? Okay, molecular weight is given, so 20.19. So the molecular weight 20.19 kg per kilomole. It is given. So right. So the work done, which it will be equal to m dot. If the enthalpy is H2, it is H1. It will be H2 minus H1, right? This is what we have to supply to the turbine. So yeah, so m dot. So m dot we have to calculate the work done. So S2 and H1 can be written as Cp T2 minus T1. We can take out T2 as common, 1 minus T1 by T2. This is m dot Cp, this is T2 1 minus P exit divided by P. Okay, this will be P1 by P2, and this will be equal to gamma minus 1 by gamma. Okay, so this is known, 3.125 10 to the power 6. Then Cp can be calculated as gamma R by gamma minus 1 into the molecular weight. This is 1 minus, this is given as 0.18, and the pressure is also given. So this is 0.264. This is 1.264. So if you, yeah, so let us calculate the Cp. This is 1.264 8314 0.264 into 20.19. So if you calculate this, you will get the value around 1900 joule per kg Kelvin. Okay, so with this you can calculate, yeah, there will be a T2. So with this you can calculate what is m dot. If you do that, you will get the value as you will get the value as 5.21 kgs per second. Okay, so I hope this part is clear, right? Any questions up till now? Any questions? Okay, so if not, yeah, Shum, you have a question?
No, sir.
Okay, so let us look into another part now. So this is, so we have to calculate what is the speed in RPM for N2O4 pump and UDMH pump. If the specific speed of N2O4 pump and UDMH pump is given, specific speed for these two cases are given. Okay, so we have to calculate the uh, the speed for these cases. So for UDMH pump, so we have specific speed is given as omega divided by q UDMH divided by g into delta h UDMH to the power 3 by 4. Okay, so specific speed for uh, this is given UDMH, which is 0.44, and yeah, so let us calculate this q dot. Q dot I we have calculated earlier for UDMH. So the flow rate we have calculated for UDMH. This is 0.11. Okay, so this is omega 0.11 divided by 9.81, and delta H is just equal to the work done work done. Okay, so this will be equal to, okay, delta H is the change in the in terms of the height, right? So this is delta P UDMH divided by rho U into G. So if you this delta P we know this is 6.68 10 to the power 6. This is the difference between the tank pressure. The UDMH has a density of 790 and density is 9.81. This is 862 meters. Okay, so we have 862 3 by 4. Okay, so with this we will get omega as 1170 radians per second. Okay, with this you can calculate the RPM for this case, which is omega is 2 pi by 60, 2 pi n by 60. So it gives you a speed of 1 okay, it gives you a speed of 11172 RPM. Okay, similarly for N2O4 it is given the specific speed is given as specific speed for UDMH is given as 0.66. Let me check it again. Yeah, it is given as 0.66. which is equal to omega q dot by g h fuel 3 by 4, right? So we have omega, this is 0.15, this is 9.81, uh, delta hf can be calculated as the pressure difference between the tank and the combustion chamber, which is 6.6 into 10 to the power 6 divided by 9.81 divided by the density. So density is 1400. It gives you 480.6 meters. So this is 480.6, 3 by 4. So we can calculate omega with this. So if you calculate omega, you will get the value as 117 radians per second in terms of RPM. You get the value as 0570 RPM. Okay, I hope it is clear, right? Any questions on this? Okay, if not, then we'll close the session for today. Okay, so yeah. Okay, so thank you all. Yeah, Shubham, you have a question?
Hello, sir. I was just having one concern.
Huh.
Sir, it was regarding the assignment question.
Hmm.
Sir, I had observed that in week 9, in solution, the first one, the question was about the actual C star. But
Sorry.
in,
Huh. Sorry, can you please? This is the previous assignment you are asking, or the current assignment?
yeah, assignment 9 quiz.
Assignment 9. This is the current one, right? Which.
Yeah, yeah.
Okay. Huh. Please go ahead.
Can I share a screen for a moment?
Sure. Please go ahead. Yeah.
Is it visible?
Yeah, it is visible. Yes.
Yeah, so like here in the assignment, the first question, it was asked to calculate the actual C star. So the answer I got was 1043, and in solution also, it was actually matched 1043.
Hmm.
But here in the answer, it's showing the incorrect.
Oh, is it? Oh, okay. I think they have made a mistake. Probably this, instead of 1043, they have misplaced at 103 1430. So
Yeah,
yeah. So
also,
again, I'll tell you this assignment part. Uh, I do not I am not concerned with the assignment. Oh, the making of the problems. I am here to discuss the problem which are similar to what you will face in the assignments. So they have a different. You can raise a complaint in NPTEL saying this, that you are facing this issue, because I'm just here to discuss the problems.
yeah, so where can I send the request like
Uh,
that? And
yeah, I think weekly you get this. Uh, uh, you get this uh, feedback form, right?
yes, yes.
There you can address this issue. So if multiple people are doing this, they'll definitely look into this matter.
Yeah, yeah, sure, sure. Thank you, sir.
Yeah. Okay. So any other doubts?
No.
Okay. Okay, so with this, probably we'll end the session. Okay, thank you all.
Thank you,
Thank
sir.
you.
Okay.